Okay, so we're back to go over some more estimations. We left off with diameter of a basketball or a volleyball or soccer ball, bowling ball. They're all about the same, okay? There are slight differences, but they're all about the same size. So for this, we want to estimate in meters. It's definitely not the size of a meter, but it's probably bigger than 1/10 of a meter. I would say somewhere in between those, probably towards the smaller side. I think a decent estimate would be 2 times 10 to the negative first meters. Height of a door. If you figure a door is just probably a little bit taller than a person, and a person on average is about 2 times 10 to the 0 meters, I wouldn't say a door is 3 meters. I can't imagine stacking 3-meter sticks and that being the size of a normal door. So I'm actually going to go with the same size as the height of an average person. Now you might say, well, obviously people have to be smaller than doors so they can fit through them. That's correct. But again, that doesn't really matter. We're just estimating, okay? We're just trying to get close to the right answer. Finally, mass of a basketball or soccer ball when it's inflated. Let's see. A kilogram is about like a textbook. A ball is definitely lighter than that. Would it be 1/10 the size? Again, possibly. I don't know. I would say that, maybe a little bit heavier than that. I would say probably 2 times 10 to the negative first kilograms. If you were thinking while I was doing any of these that, oh, that seems like a little bit too much, a little bit too small, that's fine. Okay, there's absolutely no problem with that. If your numbers, especially if your front numbers, if these numbers are a little bit off, there is no problem with that at all. What you really need to make sure of is that you're on or very close to the right order of magnitude, the right exponent on the scientific notation. So we'll move on to a new segment. Sometimes estimation requires you to calculate a few things, so we can solve the following problems by showing work and writing your answers in scientific notation. First one is volume of the physics classroom. Well, this is actually pretty simple because we already did a bunch of the relevant measurements. We said that the height of the physics classroom is approximately 3 times 10 to the 0 meters. We said the length or width, basically either way you go, it's approximately 10 meters, 1 times 10 to the first. So what I'm going to do is I'm going to take, we know the volume formula is length times width times height. We know the length of the physics classroom is approximately 10 meters. We know the width is approximately 10 meters. And we know the height of the physics classroom is approximately 3 meters. Multiply all those together. 10 times 10 times 3. 10 times 10 is 100. 100 times 3 is 300. That's 300 meters cubed, which is the same as writing 3 times 10 to the second meters cubed. Okay? So you can do calculations if you're trying to estimate like this. You can break it down into simpler measurements that you can put in calculations. Area of the football field in meters squared, okay? If you can picture the football field, we know that there's 100 yards between the end zones. And the end zones are 10 yards big, so that's 120 yards. That's a little bit too specific though, okay? And it's yards still, so it's going to be a shorter distance in meters. I'm going to say it's about 100 meters. By the way, the area formula for the football field's a rectangle is base times height. If I said that this was a cube earlier, what I really meant is make a rectangular prism. So the base, or one side of the area, let's say it's 100 meters, the width of the football field. Well, it's not quite, it's definitely not nearly as wide as it is long. Approximately how wide is it? I mean, I don't know the exact measurement. I'd say it's about maybe half as wide or half as wide as it is long. So I'm going to call that 50 meters. And so this ends up being 500 meters squared, or put into scientific notation, 5 times 10 squared meters squared. Okay, the next one is speed of Usain Bolt, the famous sprinter, during a race. So his specialty is the 100 meters. And we want the speed, and speed, as you guys will learn in a little bit, is distance divided by time, d divided by t. Well, I know that he runs the 100-meter dash, and it takes him a little bit less than 10 seconds. So 100-meter dash, 10 seconds. That means his speed is 10 meters per second, or 1 times 10 to the first meters per second. Okay? Last few examples are kind of creative problem-solving questions. Estimation can even be used to creatively solve some problems that otherwise would be tough to measure experimentally. As always, show your work and write answers in scientific notation. How many heartbeats does the average person have in a lifetime? Well, going back to our estimation of a second, we know that a person typically, on average, has 1 beat per second. That's a good estimate. All right. Now, what if I wanted to do beats per lifetime? Well, couldn't I just convert the time units until I got an answer that was approximately right for beats per lifetime? Sure, I could. I can convert seconds to minutes because there's 60 seconds in 1 minute. I could convert the minutes to hours. We know that there's 60 minutes in 1 hour. I could convert the hours to days because we know that there's 24 hours in 1 day. I can convert the days to years, 365 days, 1 year. And then the average lifespan for a person, let's say, I don't know, 70. Let's say it's 70 years. 70 years, 1 life. If you follow the units, seconds cancel out, minutes cancel out, hours cancel out, days cancel out, years cancel out, I'll be left with beats per life. So I do 60 times 60 times 24 times 365 times 70. And what I'm left with is, let's see here, we've got 2,207,520,000. But I need to put that in scientific notation, and I only need 1 sig fig. So I'm just going to keep that leading 2 and write that this is really 2 times 10 to the 9th beats per life. Now, is that exactly right? No, but it's on the order of magnitude. Somewhere between 1 and 10 billion beats per lifetime. Okay, number of dice that could fill this room. So remember, we solved this before. The volume of the physics classroom, the room volume, is 300 meters cubed. Now what about the volume of a die? Okay, a die, if you think about it, is approximately a centimeter on each side. You could probably say that, about the width of a fingernail on each side. I would say that's the size of a dice. And if it's a 1 centimeter per side, that means that it's 0.01 meters per side. So when we figure out the dice volume, dV, that would be length, width, height, that would be 0.01 meters times 0.01 meters times 0.01 meters. We multiply all those together, and we get, let's see, I'm going to put this in scientific notation, 1, 2, 3, 4, 5, 6. We get 1 times 10 to the negative 6 meters cubed. If the volume of the room is 300 meters cubed, and each die has a volume of 1 times 10 to the negative 6 meters cubed, how do I figure out how many die can fit in the room? I would divide. 300 meters cubed divided by 1 times 10 to the negative 6 meters cubed gives us 3 times 10 to the 8th dice could fit in this room. 300 million dice could fit in this room. Now, could we experimentally find that? Yeah. Is it going to be hard to get 300 dice? Absolutely. But we can make a pretty good estimate by just doing this, by using these sample calculations. And as you look around the room next time you're in it, think to yourself, does it really look like 300 dice could fit in here? That's a little surprising, but that's what the math tells us. 300 million dice could fit in this room. We'll do something similar with the number of quarters that would cover a basketball court. A basketball court, for those who don't know, is again another rectangle shape. So for the court, we have, let's see, a regulation court is about 94 feet, which means it's about 30 yards. So I'm going to say it's about 30 meters. 30 meters. And I'm going to say for the width, it's probably about closer to about 15 or so. Let's round that up to 20 just so we have 1 sig fig. 20 meters. So the court area is 600 meters squared. The quarter area, again, I'd say a quarter, I guess you could say that a quarter has a, maybe each side is about 2 centimeters. Let's do that, just for the fun of it. For the quarter area, let's say that it's So let's see here. Well, what's the area formula? Area equals pi r squared. If r is about 2 centimeters, so that's 0.2, 0.02 meters squared times pi. I'm going to call that approximately 0.001 meters cubed. So that's, let's see, 1, 2, 3. 1 times 10 to the negative third meters cubed. Now again, we simply divide 600 meters squared divided by 1 times 10 to the negative third meters squared. Sorry if I said meters cubed earlier. 600 divided by 1e negative 3. And I get about 600,000, or 6 times 10 to the 5th quarters. So it would take 600,000 quarters to cover one basketball court in those quarters, which seems like way too many quarters, but that's what the math tells us. If you were to experimentally try and do that, that's what you would find. Density of a human being. Remember the density formula is D equals M over V. Density equals mass over volume. We already estimated the mass of a human. We estimated that as about 6 times 10 to the first, or 60 kilograms. Volume of a human being is a little tricky because human's not a great shape, not a easy to measure shape, but let's be really simplistic about this. Let's say that a human is approximately the same size, or is approximately the shape of a rectangular prism. We already know the height of a human. I would say the height of a human is approximately 2 times 10 to the 0. That's 2 meters. The width of a human, I'd say, if you look at the average person's width, definitely not quite a meter, probably not even really close to a meter, maybe closer to about half a meter or so. And then if you were to estimate their the size from their front to their back, I would say that's probably a little bit less than half a meter, maybe like 0.2 or 0.3 meters. And there's our calculation. We do 60 divided by 2, divide by 0.5, divide by 0.2 again. And I come up with a density of 300 kilograms per meter cubed. Is it exactly 300 milligrams or kilograms per meter cubed? No, but you could check that and see how close you actually are, the average density of a human. The last one is going to require some reference tables, so I'm going to go grab my reference tables real quick. This last question asks for the ratio of the Earth to Sun distance to the Earth's diameter. This is from the reference tables. The Earth to Sun distance, there's a lot of interesting things on the front of the reference tables. The mean distance from the Earth to the Sun is listed right here. And it says 1.5 times 10 to the 11th. I'm going to change that to just 2 times 10 to the 11th. So that we're being more approximate. Meters. The Earth's diameter, well, the radius of the Earth is 6.37 times 10 to the 6th. But remember, radius is not the same thing as diameter. It's half the diameter. So I'm going to take 6.37 e to the 6th, and I'm going to multiply by 2, and I get about, let's see here, 12,740,000 meters. But really, I'm going to say that's about 1 times 10 to the 7th. Meters. Now I simply divide those two because that's what a ratio is. 2 times 10 to the 11th divided by 1 times 10 to the 7th, and I get a ratio of approximately 20,000. Okay? Again, is it exactly 20,000? No. In exact terms, it is, let's see here, or more exact terms. Oop, did that wrong. It's a little bit under 12,000, but 20,000 is still on the same order of magnitude. It's a fairly close estimate, and that's all we're looking for right now. We're just looking for estimates, okay? All right, so that's a little bit about estimation. The Regents typically ask questions like estimate the length of a school bus, or the length of an unsharpened number 2 pencil, or the mass of a human, or the amount of time for something to happen, and it will be very obvious which answer will be right. But if you haven't practiced estimation, you won't be very good at it, okay? So that's everything that we're doing on estimation. When you come back, I believe we'll be talking about some vector stuff. I'll see you later.